Right. So this next segment is on two other methods of doing integration. First, integration by parts, and then numerical integration. So first off, integration by parts. So integration by parts. So for example, let's say we want to integrate something that looks like this. Integrate x e to the 2x dx. So we saw in terms of the last lecture, we talked about doing it by substitution. And so let's say we want to try to do that. We could say that, okay, let u equal 2x, which means du would be 2 dx, and we have a problem because I have an x here, but my derivative is only 2, so that's not going to work. Right. Which means we could then say, well, u is x, but then we get the derivative of that is 1, and that doesn't work. So this will work by doing a substitution, so we need another way of solving this type of problem, and that way is to do integration by parts. So in terms of what that is then, you have that it is u dv equals u times v minus the integral of v du. And that is a form for integration by parts. So now we put up the problem we just had, which was find the integral of x e to the x dx. So the first thing we need to do is figure out which term is the u, which term is the dv. Right? And generally the way this will work is we want to make the u that thing which will give us the easiest derivative. Which means in this case, we're going to have u equal to x, which means dv is going to be e to the x. Actually, it was e to the 2x, so that's actually 2 in there. Let's make the problem right. There we go, 2x. Right. So now we know what u and dv is. The next thing we need to know is what is du and what is v. And so du will just be the derivative of x is 1, so we just end up with 1 dx, or just dx. V would be what we would get when we integrate e to the 2x. So we would integrate that. Again, that will be with respect to x. And we learned last week we can integrate e to the u. And so here we would say that u is going to be 2x. The derivative of that is going to be 2 dx. And so in terms of our substitution, well, we only got 1 dx here, we got 2 dx here. So my factor here is going to be 1/2. So we end up with that, 1/2 e to the u du, and we integrate, we get 1/2 e to the 2x. So now we can take all this and plug it into our process here for integration by parts. So the integral of x e to the 2x dx is given by u times v. So that would be x 1/2 e to the 2x. That part minus the integral of v, which is 1/2 e to the 2x dx. Right? So we get that. Right? So we go through and simplify this. This is going to be 1/2 x e to the 2x. Just rearranging that part. Minus, my 1/2 can come out front. E to the 2x dx. Right? And then we can do this the same way we did this earlier. We can say that u is going to be 2x. du is going to be 2 dx. And so we have 1/2 x e to the 2x minus 1/2. My factor is going to be another half e to the u du. So we get 1/2 x e to the 2x minus 1/4. We integrate e to the u, we get e to the u. So this will be e to the 2x, and then it is an indefinite interval. So we end up with that. So we got that by doing the integration by parts, we were able to integrate this thing where we could not do it by doing a substitution. So let's go through another example of this. And so let's say we now have something that looks like this. We want to integrate x sine x dx. Again, we want to do this by parts. And so we'll say u is going to be x. dv is going to be sine x. We integrate x, we just end up with 1 dx, or just dx. And if we integrate sine, we end up with a minus cosine. So now we can put this into our formula for integration by parts. And so we end up with u times v. So x times the minus cosine x. And we need to put that in parentheses at the moment because that is multiplying and not a subtraction. Minus the interval of negative cosine x dx. And so this will become a minus x cosine x. Minus and minus will actually make this a plus, the integral of cosine x. And then if we integrate cosine, we end up at sine. And so our final answer will be given by that, right? Plus c. And then again, if we actually had numbers, we could actually even then evaluate it as a definite interval. So integration by parts. Again, you want to pick it so that u gives you the simplest derivative and then go from there. Right? And then depending on the problem, you could actually end up having to do this a few times depending on how this part over here works out. You can actually do this process over and over and over. So that is another method of integrating. Another method of doing integration, because after all, integration means area. Right? And so if I have a curve of some type, so I have a curve going off something like that. We got that there is the other part of today's talk, which is on numerical integration. So, for example, I want to find the area from point A to point B. So let's say that's point A, and that is point B. And so the first rule we're going to talk about for this is called the trapezoidal rule. Which basically says I can divide this area up into a number of trapezoids and add those areas together. So I could have one going here, up to here, and I get a trapezoid there. I get another one. Unfortunately, my curve is matching to it. And then I could get another one and get that point, and so on here. Right? And then I could take those trapezoids and add them together. So in terms of the trapezoidal rule then, the formula for this is given by, so the trapezoidal rule you have, it's the integral a to b f of x dx is given by, and again, it's an approximation, so that's why the Waverly equal sign, delta x over 2 f of a 2 times f of x1 2 times f of x2 plus dot 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 f of b. Okay. And delta x is given by b minus a over n. So basically in the problem they have to tell you basically how many trapezoids are you doing. They'll have to tell you what n is here. And so let's look at an example of this. And so using the trapezoidal rule, where n equals 4, find the approximate value of this of 1 to 2 dx over x. So value dx over x is the same thing as 1 over x. And so we want to evaluate this. And so first off, we need to know what delta x is. So delta x is going to be 2 minus 1 over 4, which will be 1/4. So this method really just involves number crunching of what's going on here. And so now we start out with x naught, which is going to equal a, which is going to equal 1. And so the f of a is going to be 1 over 1, which is 1. X of 1 is going to equal 1 plus my delta x. And so this is going to be 5/4. And so f of x of 1 is going to be 1 over 5/4, which will just be 4/5. F of x2 is going to be 5/4 plus 1/4, which will be 6/4, which is also the same thing as 3/2. And so f of x2 is going to be 1 over 3/2, which will be 2/3. F of x3 will be 6/4 plus 1/4, which will be 7/4. And so f of x3 is going to be 1/7/4, which will be 4/7. And then lastly, f of x4, which is going to be 7/4 plus 1/4, which is 8/4, which of course is 2, which means this actually is my b because we are at the end point. And so f of b is going to equal 1/2. So now we've got our values of this from a to b in my increments of 1/4. So now it's a matter of just taking all the numbers and plugging them in. And so we've got, in terms of our formula, that this is going to be 1/4 divided by 2. The first term, 2 times the middle terms, and then just the last term. So 1/4/2 ends up being 1/8. This will be 1 plus, this is going to be 1/5. This will be 4/3. This will be 8/7. And then this will be 1/2. And if you plug all this in, you end up that this will come out to be 0.6970. And so that gives us an approximate answer for this particular question. So trapezoidal rule divides the area A to B in a bunch of trapezoids, which can be added together. The other method is called Simpson's rule. And now uses a bunch of parabolic areas instead of trapezoids. And generally this will give you a better approximation because after all, a trapezoid, the trapezoids we were using were now something that looked like this. They had that flat edge there. Whereas now our parabolic areas are now looking something more like that. So they are curved, and you barely run these areas where you have a bunch of alternating parabolas looking like that. And so we can look at those areas and add them up. And so in terms of the formula for this, we have, again, it's the interval A to B, f of x dx, and now it's delta x over 3 f of a plus 4 times f of x1, 2 times f of x2, 3 times f of x3 plus dot 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 f of b. And again, delta x is equal to b minus a over n. And in this case, n must be an even must be even. All right. So now let's look at the same question we just did, but now look what happens in terms of this rule. So if I do this in terms of Simpson rule, we have the interval 1 to 2, dx over x, n equals 4, and we want to do this by Simpson's rule. So we got delta x, as we had before, is going to be 2 minus 1 over 4, which will be 1/4. We can make our chart. So x naught is equal to a, which is equal to 1. X of 1 would be 1 plus 1/4, which will be 5/4. X of 2 would just be 6/4, or 3/2. X of 3 would be 7/4. And then x of 4, which would be b, is going to be 2. Okay? So we get the same chart we had before. And we do the same other steps as we did before, we evaluate. So f of a is going to be 1 over 1, which is 1. F of x of 1 is going to be 1 over 5/4, which will be 4/5. F of x of 2 is going to be 1 over 3/2, which will be 2/3. F of x of 3 is going to be 1 over 7/4, which again will be 4/7. And then f of b is going to be 1 over 2. So now we got all our values, so now we plug this into the formula for Simpson's rule. So we now end up with 1/4 over 3. 1 plus 4 times 4/5, 2 times 2/3, 4 times 4/7, and then the 1/2. 1/4 over 3 will end up giving us 1/12. So this is going to be 16/5. This will be 4/3. This will be 16 over 7, and that will be 1/2. And if you number crunch that out, you end up now with a value of 0.6933. So we see that number is slightly different than what we got the first time. And now, given that this problem was again, integral was fairly simple. After all, the integral we gave was dx over x, and evaluated from 1 to 2, and du over u is natural log, and so we would end up with the natural log of x evaluated from 1 to 2, and so this would be the natural log of 2 minus the natural log of 1 in terms of that, and so we can see how our approximation is compared to what we do if we actually did the exact integral the way it was given. So natural log of 2 minus the natural log of 1. And that number comes out to be 0.6931. So we get in terms of that. Right? So we have in terms of numerically coming up with a value of a numeral. Right? So we had in terms of integration by parts. Right? Again, breaking it out into pieces. Again, where u is the thing that gives you the simplest derivative. And then in terms of these two numerical ways of giving the interval, whether it is the trapezoidal rule or Simpson rule. And that will conclude this lesson.